Now we're going to talk about surface integrals of vector fields. Our last surface integral topic will be surface integrals for vector fields. But first, we need to make sure we understand what it means for a surface to be orientable or two-sided. A surface that is orientable is one that allows us to choose a direction for our normal vector that remains consistent at each point on the surface, regardless of how we traverse the surface. If I imagine walking along a surface starting at a point P on the surface, and if we got back to our original starting point, we're still oriented just as we were when we started out, then our surface is considered to be orientable. On the other hand, if I have a surface that is not orientable, I'm going to find myself oriented differently when I get back to my original point. An example of that is the Mobius strip. If I were to start out walking along my Mobius strip, as I move along, when I get back to the same point I started at, my orientation is opposite to what I started with. This gives me a surface that is not orientable. In other words, I don't have a distinction between my surfaces. They're not two-sided. One surface turns into the other surface as I move along the surface. Orientable or two-sided surfaces have two distinct sides. This means that at any point P on the surface, I have a choice of two normal vectors. I can have a normal vector that points outward or a normal vector that points inward. And often I have to choose between these two normal vectors. Once I've chosen the side that I'm going to work with, my surface becomes oriented. By convention, when I have a surface that is a completely enclosed region, I want to choose the orientation so that my normal vector always points outward. If I have a surface that does not enclose a region, I'm going to have to specify what that orientation is. This is just a simple matter of stating the direction that my normal vector points in. For example, I might say that it points in the positive x direction. In our parametrization process for a surface, we found a normal vector that was given by t sub u crossed with t sub v. For many surfaces, the normal vectors will be consistent with a specified orientation, and I don't have to make any adjustments to ensure a fully oriented surface. But occasionally there will be surfaces where n is equal to t sub u cross t sub v that is not consistent with a specified orientation. In this case, the sign of t sub u cross t sub v will have to be reversed before I can do any computations. The most common surface integral of a vector field is the flux integral. The flux integral gives me the total scalar value of the flow or transport of something across the surface. If my vector field f and the normal vector are aligned at a point P, which means the angle between f and my normal vector is 0, then the component of f in the direction of n is f dot n, which is the magnitude of f. And this tells me that all of f flows across the surface in the direction of n. If the vector field f and my normal vector point in opposite directions at the point P, meaning that the angle between f and n is pi, then the component of f in the direction of n is given by f dot n is equal to the negative of the magnitude of f, which means that all of my f flows across the surface in the direction opposite of my normal vector. If the vector field f and the normal vector are orthogonal to each other at the point P, meaning my angle theta is pi halves, then the component of f in the direction of n is f dot n is equal to 0. This means that none of f flows across the surface of the point P. If I'm given a smooth oriented curve S that is parameterized as r of uv is equal to a vector with components x of uv, y of uv, and z of uv, where u and v vary over a region r in the uv plane, a vector normal to the surface is given by t sub u crossed with t sub v, which we assume is consistent with the orientation of S. Unit vectors are always easier to work with, so I'm going to use n is equal to t sub u cross t sub v divided by the magnitude of t sub u cross t sub v for our unit normal vector with the same orientation. so that my double integral over S of f dot n ds is equal to the double integral over r of f dot n times the magnitude of t sub u cross t sub v dA can now be written as the double integral over r of f dotted with t sub u cross with t sub v divided by the magnitude of t sub u cross t sub v times the magnitude of t sub u cross t sub v dA. But my magnitudes of t sub u cross t sub v cancels, leaving me with a double integral over r of f dotted with the cross product of t sub u crossed with t sub v dA. T sub u crossed with t sub v is equal to the vector with components negative z sub x, negative z sub y, and 1, so that my flux integral now becomes the double integral over r of the quantity minus f times z sub x minus g times z sub y plus h dA. If I let f be given by a vector with components f, g, and h, and this is a continuous vector field on a region of R3 containing a smooth oriented surface S, if S is defined parametrically as r of uv is equal to a vector with components x of uv, y of uv, and z of uv, for uv in a region R, then the double integral over S of f dotted with n ds is equal to the double integral over r of f dotted with t sub u cross t sub v dA, where t sub u is equal to a vector with components the partial of x with respect to u, the partial of y with respect to u, the partial of z with respect to u, and t sub v is given by a vector with components the partial of x with respect to v, the partial of y with respect to v, and the partial of z with respect to v, and these are continuous on R. The normal vector t sub u cross t sub v is non-zero on R, and the direction of the normal vector is consistent with the orientation of S. If S is defined in the form of z is equal to g of xy for xy in a region R, then my double integral over S of f dotted with n ds becomes the double integral over R of the quantity negative f zx minus g times zy plus h dA. Let's work an example. I want to find the flux of the vector field given by f is equal to a vector with components x, y, z across the slanted face of the tetrahedron given by z is equal to 10 minus 2x minus 5y in the first octant. We're going to assume our normal vectors are in the positive z direction. Using z is equal to 10 minus 2x minus 5y, I get z sub x is equal to negative 2, z sub y is equal to negative 5, and x is equal to 10 minus 5y divided by 2. My normal vector is t sub u crossed with t sub v, and this is a vector with components 2, 5, 1. So that my double integral over the surface of f dotted with n ds becomes the double integral over r of f dotted with t sub u crossed with t sub v dA, and this becomes the double integral over r of the vector with components x, y, and 10 minus 2x minus 5y dotted with the vector with components 2, 5, 1 dA. This can now be written as an iterated integral from 0 to 2 of the integral from 0 to 10 minus 5y over 2 of 2x plus 5y plus 10 minus 2x minus 5y dx dy. This gives me an integral from 0 to 2 of an integral from 0 to 10 minus 5y over 2 of 10 dx dy. I work with the inner integral first, and I get an integral from 0 to 2 of the quantity 50 minus 25y dy, which becomes 50y minus 25 halves y squared evaluated from 0 to 2, and it gives me 50. This is the flux of my vector field. Now you get to try it. Pause the video and find the outward flux for the following heat distribution and surface. When you're ready, restart the video to check your understanding. The heat flow vector field for conducting objects is given by F is equal to negative K del T, where T of xyz is the temperature of the object, where K is equal to 1. Compute the flux of F for the temperature distribution T of xyz is equal to 100 times e to the negative x squared minus y squared minus z squared power across the surface S, where S is the sphere given by x squared plus y squared plus z squared is equal to a squared. I want to use x squared plus y squared plus z squared is equal to a squared to solve for z. I get z is equal to the square root of a squared minus x squared minus y squared, so that tu cross tv will be equal to a vector with components x over z, y over z, and 1. F is equal to negative del t because my k is equal to 1, which is equal to the negative of a vector with components t sub x, t sub y, t sub z. This gives me a vector with components 200x times e to the negative x squared minus y squared minus z squared, 200y times e to the negative x squared minus y squared minus z squared, and 200z times e to the negative x squared minus y squared minus z squared. My double integral over s of f dotted with n ds becomes the double integral over r of my vector with components 200x e to the negative x squared minus y squared minus z squared, 200y e to the negative x squared minus y squared minus z squared, 200z e to the negative x squared minus y squared minus z squared, dotted with a vector with components x over z, y over z, and 1 dA. 200 e to the negative a squared is a constant, where negative x squared, negative y squared, negative z squared is negative a squared, so that I can bring that term out. I get 200 e to the negative a squared times the double integral over r of the vector with components x, y, z, dotted with a vector with components x over z, y over z, and 1 dA. This gives me 200 e to the negative a squared times the double integral over r of x squared over z plus y squared over z plus z squared over z dA. I can rewrite this integrand to give me 200 e to the negative a squared of the double integral over a squared over z dA. Now, using symmetry, I notice that I can integrate the top half of my sphere and double it to find my flux. I get 200 a squared e to the negative a squared of the integral from 0 to 2 pi of the integral from 0 to a of 1 over the square root of a squared minus r squared, r dr d theta. This gives me 400 pi a cubed e to the negative a squared. My total flux will be twice this amount. I get 800 pi times a cubed times e to the negative a squared as my flux for my temperature distribution over the surface of my sphere. This is how I can work with surface integrals that involve vector fields. Be sure and let me know if you have any questions.